Welcome back, everyone, to the deep dive. Today, we're plunging into something pretty fundamental. It's everywhere, but often unseen. Mechanical system design for buildings. You probably know it as MEP.
That's right, MEP.
Yeah, these aren't just, pipes and wires stuffed in walls. They're the guts of a building, really.
Yeah,
The crucial systems making everything comfortable, safe, functional.
absolutely. Functional is the word.
Okay, so let's unpack this sort of silent orchestration.
Well, what's really fascinating about MEP, I think, is just the sheer breadth of it. And more importantly, how it all has to fit together perfectly.
It's not just one thing, then.
No,
Yeah.
no. When we talk MEP, we mean mechanical, electrical, plumbing, HVAC, that's heating, ventilation, air conditioning, and fire protection systems.
Wow, okay. That's a lot.
It is. And while today we're maybe focusing more on the mechanical side,
Right.
it's really vital to remember that the electrical, the plumbing, fire protection, they aren't just like neighbors in the building. They're deeply interwoven. They have to be.
So they all affect each other.
Massively. I mean, the coordination, that's where the real engineering challenges pop up. And frankly, the most elegant solutions too.
So the engineer's job is...
Well, the core role is making sure every single one of those systems works in harmony, like a well-oiled machine. Plus, they all have to meet code, obviously,
Obviously.
and support efficient, safe construction, and deliver a great indoor environment at the end of the day.
That coordination piece sounds critical. I was reading somewhere that even things like insulation choices or the type of windows
Oh, absolutely.
can massively change the HVAC load. So the
Yeah.
mechanical design actually starts way earlier, like in the architectural phase.
Spot on. That's a huge point.
Yeah.
The mechanical design isn't done in a vacuum. It's a direct response to those architectural decisions, and what the building's actually going to be used for.
Right, right.
So when we dig into the mechanical stuff specifically, we're talking about designing the building's heart and lungs, essentially. Heating, cooling, ventilation systems, and making sure the air quality inside is, well, optimal.
Okay, the heart and lungs. I like that analogy. How did that design process actually work?
It's incredibly detailed. It really starts with calculating heat loads very precisely. We look at things like building orientation, which way it faces the sun, how many people will be inside, heat from computers, lights.
All that internal stuff adds up.
It does. And the outside climate data, of course.
Yeah.
We feed all that into pretty sophisticated energy simulation software. BIM, building information modeling, is key here too. Yeah, lets us predict energy use, model airflow really accurately, helps prevent issues like, sick building syndrome or just annoying hot and cold spots.
Well, it's way more than just setting a thermostat. It's managing the air itself, the invisible stuff.
Exactly, managing the invisible.
Okay, so once you've got those load calculations, how do you pick the actual equipment? It's not just like grabbing the biggest air conditioner off the shelf, I assume.
Definitely not. Selecting the right machinery, chillers, boilers, maybe air handling units, AHUs, it's critical, yes.
Yeah.
But it's about so much more than just raw power or capacity.
Like what?
Well, you're balancing efficiency targets, noise levels. Nobody wants a loud system. How easy it is to maintain, even just where you can physically fit the equipment.
Space is always an issue in buildings.
Always. And, optimizing the AHU performance is one thing, but often the real artistry, you could say, is in designing the duct layout.
The ducts.
Oh,
Really?
yeah. It's this complex puzzle. You're balancing airflow rates, pressure drop, sound, fire safety, all within the building structure.
Yeah.
A badly designed duct system, it can just kill the efficiency of even the best, most expensive equipment.
Huh. Never thought about ducts that way.
Yeah, it's intricate. So the key focuses through this whole design process, always ensuring comfort for the occupants, maximizing efficiency, how much energy it uses, and really pushing for sustainability.
Sustainability.
Yeah.
You mentioned things like heat pumps and VRF systems earlier. Variable refrigerant flow.
That's right. VRF.
They seem to be everywhere now. But what's the biggest sort of trade-off engineers face? Trying to hit those ambitious green targets, but also staying within budget. Are these newer techs always the best choice?
That's a really crucial question. Modern systems like, high-efficiency heat pumps, VRF, they offer significant energy savings, absolutely. More flexible, too. But they often have a higher upfront cost.
The initial investment.
Exactly. So the compromise, the trade-off, it often comes down to balancing that initial capital cost against the long-term operational savings, the running costs.
Yeah.
Sometimes, a project might have to go with a slightly less efficient, maybe more traditional system because of the budget.
Okay.
But then they might try to compensate with smarter controls, maybe more advanced zoning, to lessen the long-term energy hit.